machine learning experiments that have actually been done to try to predict the solar cycle. And there's some really, really cool stories here. So we've got sort of three stories. We've got our generalized machine learning methods. Think of anything you can pull out of scikit-learn. Literally, that's where they're getting these. Astronomers had been using Python for quite some time to process all of their data, so we were very agile in being able to deploy these type of machine learning methods, especially when they're as accessible as something like scikit-learn, or sklearn, yeah, scikit-learn. Even further into Keras, which is, for deep learning, very accessible, and then eventually into PyTorch, which we'll talk about a little later. We've got our first three samples, which correlate with 1, 2, and 3, which you'll notice kind of sit off on their own little islands in the top corner. Those are all basic LSTM models. Call it stacked, call it single layer. They're using LSTMs with multi-layered solar data, so multiple data points at any one time, to try to predict the next solar cycle. This comes with its pros and cons. The major con being that you really don't have an error bar associated with the data. You can do some ensemble modeling to get an error in time or an error in magnitude, but you really can't get both, and it's just, you don't have the confidence there. You'll also notice that all of those are kind of off to their side in their own space. Where we really see a cool jump here is with the Bayesian LSTM. That one not only took into account the error in the data innately, but also took into account its own ability to generate an error, not using ensemble modeling, using Bayesian techniques. So you'll see that one will actually land about in the middle of where we're seeing the rest of our models land, which is typically a good indicator in physics. You've got multiple models saying the same thing, you've probably found the right answer. In machine learning, that's a little more, maybe they're all picking up on the same feature, but to physicists, this looks great. So we talked about basic scikit-learn models. We talked about sort of that LSTM evolution, where we're not only just maturing as a field and using deep learning, but also evolving it to fit our data better. The last one I want to mention is really special to me because they use a very similar technique to what we did with refit. So in refit, we took a ResNet 50 image classifier, find a cat or dog, and we cut the bottom off of it and used it as a k-nearest neighbor encoder for supernova explosions. This was a crazy idea. We had so many people tell us this was a bad idea, and it totally worked. This group used WaveNet. And you're like, what's WaveNet? So WaveNet is effectively an encoder for audio data. So you've got your literal audio wave profile, you run that through the WaveNet encoder, you get an encoding space. Now obviously you could use that for classification or transcription or something of that nature. Spectrographic data is a wave. It's measured in nanometers. Radio and sound just happen to be measured in hertz, but it's, at the end of the day, it's the same unit. So it's sort of an intuitive use, just sort of out of the box for the use case. So they took WaveNet, they cut the bottom off, and they used that as an encoding for an LSTM input.